Thank you. So, welcome to Things I Learned Writing Code Generators for almost a decade. I'm Ioannis. I'm a graduate of the Computer Science Department from the University of Ioannina. So it's a really great and special day for me coming back to the city. I graduated 21 years ago, almost, and ever since I've been working as a software engineer, mostly writing code in Java. The last 12 years I've been doing that, being part of Red Hat, where I mostly work on open source projects. I'm also a member at the Apache Software Foundation, where I've been involved in numerous open source projects, including Apache Camel, Carafe, Service Mix, and more. I've also created a few open source projects myself. The most noteworthy is Spring Cloud Kubernetes, the Fabricate client for Kubernetes, Decorate, and the last couple of years I'm focused on a very cool and modern project called Quarkus that aims at making Java more lean, more fast, and more fun to use. So I would say that over those 21 years, I've become really good at writing really bad code that generates cool stuff. And those experiences I will try to communicate and share with you here today. But why did I went with this topic? Usually, even though I'm not a professional speaker, I tend to give 1 or 2 talks per year in order to promote the projects and the products I'm involved. So you could say that my talks usually have a sort of product placement. And by the way, this is how AI generation perceives the phrase product placement. But, coming back to this city, I felt that it's a great opportunity for me to try and have a somehow wider reach and not just limit my talk to Java developers, but, to talk to things that will be relatable to all software engineers. An additional trigger for me was a recent meeting that I had where we were trying to troubleshoot some issues we had in an open source project that was heavily relying on code generation. So during this meeting, there was a colleague of mine that went, hey, this is clearly a bad practice that we are employing here. We should change that. And that was a trigger for me because I don't believe that there are such things as good or bad practices. I believe in decisions that are either well or poorly thought. And if it is one thing that I would like you to take from this presentation, it really is that. There's no good or bad practices. And this message is especially important nowadays because our industry is becoming very fashion-driven. And we see everyone trying to religiously follow what the big players are doing, what Netflix does, Spotify, Amazon, or individual influencers in the space. And we often forget to evaluate what are the needs of our project, what are the idiocracy of our team, what fits best the mentality of our team. So I thought that it would be a good idea to give a presentation and talk and share a little things about the whys, the hows, and the whats that applied in our case, and share this information with you in order to get you to become more critical when it comes to code generation. I feel that this will be a presentation that would be useful to you, even if you don't intend to write and implement code generators anytime soon, but even if you just use and want to, make the most of the code generation tools that you're already using. So, how did I get into code generation myself? It was 2011. I was working on a project called Fabricate, and I was part of a very strong and talented team. The thing was that people in that team had the tendency to express their talent in a very unique way. So even when it came to things like design patterns, which are usually employed in order to provide a common understanding of how we are doing things and provide a common vocabulary, you could see that different people in that team were approaching the design patterns with a completely different way. So for example, we were using 3 or 4 different variations of the very famous builder pattern. Sometimes those changes were stylistic, but other times those variations also were behavioral, which was a source of problems because when you were using a pattern but one time was behaving one way and the other was behaving another way, often caused issues and was sometimes the source of bugs. So at some point in 2014, I was returning from a conference. I was sitting at the airport with a colleague of mine, and he started coding something on his laptop. And I asked him, hey, what are you doing? And he said, I'm writing a code generator that I want to use in order to solve problem X. So I felt that it was a great opportunity for me to follow along, take out my laptop, and start building a code generator that would generate builders for my Java objects in order to use that generator to enforce a common style of builders in our project. Which brings us to reason number one on why it's a good idea to use or implement your own code generator, and that is consistency. So, did it work? I would say that it would have worked, but unfortunately, our attention was shifted elsewhere. As I mentioned, it was 2014. Kubernetes just was announced by Google, and as a good fashion-driven team, we decided to ditch everything we had and standardize around Kubernetes, starting from ground zero. The thing with Kubernetes is that it provides a very rich domain model consisted of plenty different objects that were pretty complex and very deeply nested. Models like that are not usually expressed that well when you deal with a language that is as verbose as Java is. So we had to create multiple different objects and then call setters on those objects, combine those objects together in order to create an object graph that represents those Kubernetes entities. And that was as painful as you can witness in that code snippet I'm sharing with you. So it occurred to me that maybe it's a good idea to take off the shelf the proof of concept that I implemented but never had the chance to use and apply it to the Kubernetes entities in order to have a fluent style of creating objects. The end result looks a little bit like this, which is far more readable than this, easier to maintain than this. You typically have less objects to deal with, so you gain readability, assistance from your IDE, because you get things like code completion and stuff, less imports to manage, but most importantly, this structure matches one-to-one with the structure of the actual Kubernetes objects. And kids, this is pretty much how I started writing code generators at my day job. Now, the thing with the Kubernetes domain is that it is huge. And even though we came with a very good strategy and a very good approach on how to create fluent builders for our objects, we still needed to figure out a way of creating the Java representation of those entities in the first place. Even though Kubernetes did provide an open API definitions that we could use in order to generate those objects, convert those objects to Java, we found that a lot of information was lost in the translation from the Kubernetes model to OpenAPI and from OpenAPI to Java. So we felt that it might be a good idea if we implement our own generator that would parse the Kubernetes entities, which are originally implemented as Golang structures, and then generate JSON schema. And since it was 2014, there were plenty of tools out there that would perform conversion of JSON schema to the language of choice. By the way, this means that by getting our hands to an intermediate representation of the Kubernetes model, we had the ability to easily move from one language to another, which brings us to the next reason on why it's a great thing using or writing code generators, and that is polyglottism. Now, did it work? Yeah, I would say that it worked. The Fabricate Kubernetes client at the moment is thriving. It has hundreds of active contributors. It has thousands of stars on GitHub, and it's pretty much the most commonly used framework for Kubernetes implemented in Java. Now, when you acquire a skill that you find immensely useful on your day-to-day, you constantly ponder about other areas where you can apply this skill to. So we wanted to find where else we could use code generation in order to gain value. The framework that we created not only provided the ability to easily construct and manipulate Kubernetes objects, but it also provided a domain-specific language which allowed users to easily communicate with the Kubernetes API server. The DSL looks like that. If you encounter the term DSL for the first time, DSLs are specialized computer languages, not to be confused with programming languages. They are usually implemented on top of an existing programming language, have a very specific focus on a particular domain, in our case, Kubernetes, and usually are provided and implemented as an API that allows you to chain functions or methods together in order to allow users to create expressions that resemble natural languages. I just shared an example with you. Another example is the fetch API of JavaScript, which is DSL. Now, what it means and what it takes in order to create a DSL. We thought that we should experiment with that, and we should pick up, let's say, more compact domain than Kubernetes itself. So we started experimenting in the Docker domain, and we tried to create a DSL for writing and implementing a Docker client. Usually when you go and try to create a domain-specific language, you need to decide which are the method chains that you're going to allow. Then you model those chains in a structure that is tree-like, where each node of this tree represents a method call or a function call and stuff. And then you need to have a strategy of converting those nodes to either structures, classes, interfaces, depending on the language that you use. Now, the goal here is not to make you experts on DSL authoring, but the message that I'm trying to pass is that writing a DSL can be a tricky and complex stuff, and also the larger that tree becomes, the harder it is to implement, the harder it is to evolve, to change, and also in some cases where language constructs like generics and stuff are involved, things are becoming much more complex. All in all, domain-specific languages are something that are pretty elegant, pretty cool to use, but have a high maintenance cost. Being able to lift that maintenance cost off your shoulders promotes maintainability and makes your project easier to move forward and to evolve. So, did our approach work? Yes, I would say that it did. We created the Fabricate Docker client with the aid of our DSL generator, but unfortunately, we were never able to port and use that DSL generator in the Kubernetes client, which was our original goal. That was mainly because teams changed, reorganization happened, priorities shifted, and stuff like that. Worth mentioning, however, that this DSL generator may or may not have been an inspiration for some scientific papers we've seen flying around that were touching the topic of domain-specific language generation. So to recap, why would anyone would like to use or implement code generation techniques? Besides the obvious reasons, you write less code and things like that, it's easier. We get consistency, maintainability, and polyglottism. Now that I'm pretty sure that I sold the concept to you successfully and you want to go home and start writing code generators, I would like to say a few things on the how. Usually when someone tries to get into code generation, the first thought is to use templates. Templates are like mold casting. They have a structure that resembles the final code, but they do have some placeholders where you're able to fill in with your parameters. An example of template looks like that. It's actually a template, a real template I'm using in one of my projects, which looks like the end code, but does have some placeholders designated by the $ and the squiggle brackets. Great thing about templates, they're very simple to read, very simple to use, easy to get started, and have a minimal learning curve. But when we move to more complex examples, like this one, which also includes assignments, conditionals, and things like that, we really notice that we lose on readability. And another thing that you may or may not have noticed is that we no longer get that syntax highlighting, which is another issue with templates. Our code generators initially were based on templates like the ones that I shared with you. And one of the constant struggles that we had was that it was very hard for us when we were authoring those templates to understand if the rendered code will be able to compile, if the rendered code will be syntactically correct or not, and things like that. Also, we just witnessed poor tooling support. We didn't have syntax highlighting. We lacked code completion and things like that. And I know that nowadays modern IDEs have partial support for some template engines, but this is not always the case. But what was the biggest issue for us was that as our code generation techniques were becoming more sophisticated, we were losing on readability on the final template. They were becoming very complex, very hard to maintain, and it was a pretty lousy experience. This was not just our experience. I think that this is the experience that pretty much everyone has, which led some template engines authors to that realization and forced them to a direction of implementing logicless template engines like Mustache, which is one of the most prominent examples. The idea behind logicless template engines is that we limit the scope and the features of the template engines itself in order to prevent users from creating horrendous templates that will be impossible to maintain and then curse the template engine authors. Are there alternatives? Yes, there are. There's the possibility of using more specialized tools for the job. This is what I call by specialized generators. Usually they come in the form of libraries which allow you to create and manipulate the AST of your, the abstract syntactic tree of your language and then allow you to render code. And such example is listed here. This is an example of Jennifer. It's a template, is a specialized generator for Golang, which one can use in order to create a main file and throw in a main method that does fnt println hello world. Another specialized generator is the one that we used and we implemented in order to power and fuel our builder and DSL generators, which looks like that. We use a fluent builder style in order to create an interface that we call getter, and then we add a new method called hello world, and finally we are able to call the render method and print the render interface on screen. So when would one use a template engine, and when would try to go to a specialized generator? I would say that if your needs do not allow you to use a specialized generator, you have to go to a template engine. And when this is not possible, I mean to use a specialized generator, is when one is not available for your languages, or when you need to generate code in many different languages or many different file formats. In those cases, it doesn't make sense to use something specialized. You have to use the more generic approach, which is going for templates, which is also the main reason that most project generators that don't generate just single source files, but generate full projects with config files, with build files, and support for many languages, are usually implemented using template engines. The most popular example these days is Backstage, which is a tool that allows platform engineers, among others, to create and define software templates for their teams to use, and those software templates are usually implemented in an engine called Nunchucks, written in JavaScript, I think. So the great thing about using the specialized generators over templates is that they provide you and they give you the ability to leverage the strengths of the computer programming language that you're already using. You're able to use flow control, you're able to use lambdas, you are free to reorganize the code exactly as you want, split it in multiple files, use the composability and reusability features of your language, which is a very cool feature. Lately, we see that there are template engines that try to steal that feature from specialized generators, and they allow the implementation of things like directives in the computer language of choice in order to extend the capabilities of the template engine. The bad things around specialized generators is that they are more verbose and they do have some learning curve. A third category that I will briefly just mention is using parsing or refactoring tools. I will mention OpenRewrite, which is a refactoring framework. It mostly focuses around Java, but I think it supports some other languages too, which allows you to take existing code and perform modifications to that code. And also I'll mention Tree-Setter, which is a family of parsers for pretty much, I think, most of the popular languages. It is pretty popular for implementing tools like syntax highlighting and IDE-related tools, but they can be used in order to parse existing code and perform minor manipulations. So it works pretty well. So to address the elephant in the room, what about artificial intelligence and LLMs? I will keep that part for the end of this presentation, not because I want to build up anticipation, but because I would like us to first understand a few things about dealing with generated code, which I think it's really important. When you deal with generated code and you have to do, the day-to-day, that often involves debugging the generated code, using your IDE to perform inspections of the generated code, code completion, things like that. In more rare cases, to edit generated code, but most importantly, to deal with incompatible code changes. What are incompatible code changes? Let me share with you a diagram which pretty much tries to describe the flow of things when we were generating code for the Fabricate Kubernetes client. Our input was the Kubernetes domain model. It was fed to the code generator, and that outputted the Java representation of the Kubernetes model that was consumed by the Kubernetes client and then used by downstream projects like Spring Cloud Kubernetes, Decorate, Quarkus, and more. Each time a new version of the Kubernetes model came out, the Java representation of the Kubernetes model was changed. But also, each time we released a new version of our code generator, a new version of the Kubernetes model for Java was also generated. Often, we had the unpleasant experience of having breakages when this update happened in all downstream projects. Kubernetes client, Spring Cloud Kubernetes, and more. So, how do you deal when you have to such incompatible code changes? Well, unfortunately, the answer is that sometimes dealing with incompatible code changes is inevitable. And if you can't avoid dealing with the incompatible code changes, then you better be prepared to properly communicate to all downstream projects that an incompatibility has been introduced. What we found out is that using semantic versioning is a very effective way of communicating things like that. Are we all familiar with the concept of semantic versioning? Well, there are some. The idea behind semantic versioning is this. It's a convention used for versioning software components. The idea is that you split the version in 3 parts: major version, minor version, and patch version. Each time a change that does not affect the public API of your component takes place, you're free to bump the patch version. Each time you add things to the public API, new features and stuff, you're able to bump the minor version, but each time you modify the public API or you remove things from the public API, you bump the major version. This allows everyone that uses the code that you just generated to know that they should expect, whenever they see a major version change, that they should expect, a lot of changes that would potentially break their project, and that they would have to spend time and do some maintenance work in order to align their code to the changes in the generated code. The thing with semantic versioning and code generation is that it is very hard to implement because you don't have direct control over the code that gets generated. So that often leads to unintended changes creeping to the public API of the software component that you have. And usually such cases often produce a load and unscheduled workload. So one solution that I'm a strong advocate of is to check the generated code in version control. And this is something very important, and it's something that you may want to consider even if you don't write the code generator yourself and you're using existing code generator tools. Of course, this is a pretty controversial topic, and there are a lot of people arguing to that. However, I feel that it is an approach, and it worked very great for us because it allowed us to track changes. It was an enabler for semantic versioning, and on top of that, we had added benefits like our IDE was able to easily detect the generated code. One issue we had in the past was that we often used to generate code as part of the build, and often the IDE was unable to see where the actual code is. And even when some people in our team were using tools like IntelliJ, which allows you to go and explicitly specify those paths, it often didn't play nicely. And of course, when you get the code on version control, it is easier to find when you do things like debug and things like that. Most importantly, it forces you to just generate code whenever you have to. And this is very important because you make your builds become way faster because you don't constantly regenerate code that you don't need, and it also saves the environment of unneeded carbon dioxide emissions. Now, the bad things about the generated code are usually evolve around those axes that, hey, by doing that, developers may suit their own fit because, you know, they may try to manually edit the generated code and then rerun the generated code and eliminate their changes, or they may do something stupid that could potentially cause the generated code to become out of sync with the actual model. Nowadays, however, I think that both of these are non-issues because with the use of CI tools like GitHub Actions, GitLab pipelines, and stuff like that, you can enforce and guarantee that your generated code will be always aligned with the model. And I'm not sure if I have internet, but let me try that anyway. Because I would like to share with you an example, a real-world example that we are using in a project. This is a GitHub action that each time we bump the model in the project definition, we automatically run a generate script that then creates a pull request in order to submit the generated code back to the repository. And this is something that worked wonderfully for us. Now, of course, there are cases where it might not make sense to get the generated code inside version control, and I'm referring to cases where the generated code constantly reacts to the actual code of your project. Most common example is when you do things like transpilation from TypeScript to other languages and stuff like that. Once again, there's no one-size-fits-all, and there is no good or bad practices, and you need to, to evaluate what's best for your team and what's best for your project. So let me recap. When you deal with generated code, it is really important to have a strategy for detecting when the generated code changes, when the API that you will share with your colleagues, with other teams, will change. If you can't prevent changes and if you can't prevent breakages, you need to be able to properly communicate them. And it's always a good idea to only trigger code generation whenever you have to. Save the environment. So that brings us to generative AI, LLMs, and things like that. I'm pretty sure that most of you have already used artificial intelligence, ChatGPT, and stuff like that in order to generate code. Is there anyone that hasn't tried that? Okay, that might be embarrassing for some people. Is there anyone that has tried something like that? Raise your hands. So you've already realized that this is something that works really well. However, it's still not perfect. I tend to prefer using AI and stuff like that, not for code generation that takes part, let's say, as part of the build, but mostly as assistant to our IDE editor and stuff like that. So I tend to prefer using tools like GitHub Copilot, Codium, and projects like that. Worth mentioning that I really like Codium, mostly because they advertise that they train their model using only projects, open source projects with permissive licenses, which is, feels more ethical compared to what Copilot does. So you already know that while most of the time AI can get the code right, there is no guaranteed result. There are some times that it's not very accurate. But most importantly, you most probably have already realized that the generated code is not deterministic. You may try and regenerate the same prompt again and again and again, and you may be getting most of the time something like this, but every now and then a difference like this. These are two Python functions generated with a prompt like, hey, create a function that prints hello world. And most of the time, that function may be called greet, but once in a while, it may be called, say, hello. And even if you try to address this issue in the prompt and specify the name itself, there might be times that it will ignore the prompt and go and do its own thing and name the method with the random gibberish thing. Oh my God, where did my image go? Anyway, let's go back to the previous slide then. So what I'm trying to get at is that AI, due to the lack of idempotency and the lack of determinism, can often introduce unneeded incompatible code changes to the generated code, and this is something really bad. And also, sometimes it can even produce code that doesn't even work. And here, where I'm missing the image, which is called and named AI facepalm, is an unpleasant experience that I had a couple of months ago, where I was invited in a podcast to do some kind of demonstration, and I wanted to show them some Quarkus CLI plugins that I've implemented, and I thought that it would be very cool if I demonstrated a CLI plugin that would generate Java code. And even though I rehearsed it tens of times and it was always working perfectly, during that demo, it barfed, like the image that I intended to have in this presentation, and it was a very unpleasant and embarrassing experience. So I would say that LLMs are not just yet ready for being used for, let's say, unsupervised code generation. But if you're stubborn enough, like I am, and you want to try that anyway, then you may want to consider using tools like LangChain, which might allow you to hook in custom tools that either may enforce style, contract, correctness of the code, or alignment with what you already have in your repository. To give you some more details about the unpleasant experience that I had, I wanted to generate an entity, and I requested, hey, give me an entity being for a person, for example. And while it did generate the entity correctly, it used imports that were not aligned with the dependencies that I had in my project. So, for example, I was using the recent Jakarta API for JPA, and it decided to use the imports of the old Javax persistence imports and stuff like that. So, using additional tools that you can use to guard and prevent situations like this might produce somehow better results than the ones that I experienced. So let me recap. Code generation is something that leads to efficiency. Usually people go about creating software templates, and then when their needs increase, they move to specialized tools. It's always a good idea to only generate code when you have to and when you need to, and you always need to have a strategy for tracking changes. And of course, AI, in my opinion, is not there just yet. Some links, you can find Both this presentation and pretty much all my presentations on GitHub, under my repository, my org, the repository is called Presentations. Sandrio was the code generator that was implemented and mostly referred throughout this presentation, and the Kubernetes client, which was, the subject where we applied code generation to, can be found on this link. So do we have questions? Thank you.
Thank you for that. So any questions before we go on to a break? Okay, so we have a question over here.
Not him.
Not him. Why not him?
Okay, no, please go on. I'm just joking.
About testing the generated code.
Yes.
A question about testing the generated code. You prefer to test for text properties of the generated code or compile and run stable programs?
I would say that we do both, and we were also forced to test some of the most popular downstream projects too, just to have an additional way to guard against breaking downstream projects. So sometimes we use simple unit tests that perform the code generation action and then try to parse and see what was generated. In other cases, we use in the unit test the generated code itself, just to make sure that it functions, not just looks as we expect, but it also functions as intended. And the last is what I mentioned with downstream projects. So we build our project, then we get the snapshot version we just built, apply it to downstream projects, and make sure that they also compile.
Okay, so any other questions? No? Okay, so we have an opportunity to go outside, get a stretch before we come back in here in about 5-10 minutes. See you all back here soon.